Today we're going to be covering volumes of solids of revolutions. So we're still doing volumes of solids. This time the solids are going to be formed in another way. Alright? So volumes of solids. We will remember our basic formula for every volume. And that is the integral of a cross section's area times a little width, right? Cross section area times the width. Alright? Okay, let's consider this region R. It's no longer the base of a solid. Now we're going to take this region and we're going to revolve it around an axis. So in this intro, we're going to revolve that region around the x-axis. So imagine this region being revolved around the x-axis and it forms a solid. It forms kind of a conical solid. If I were going to try to sketch this graph, let me get a pencil out. If I was going to try to sketch this graph, I would take this and it would be revolving around, so it would have this image on the other side, and it's a revolution, so it does like that. Kind of a bugle shape or a horn shape, okay? Something like that. So we need to find the volume of that solid. Each cross section is perpendicular to the x-axis. And each cross section, what is each cross section here? Each cross section is a complete circle. So the area of a cross section will be pi r squared. So the volume of that solid would be the integral of pi times r squared dx, where r is top minus bottom, just like before. Okay? Let's consider this region. Let's once again revolve this region around the x-axis. I like to put a dashed line on my axis of revolution. Now we're going to revolve this around the x-axis, and it's going to get a little bit more difficult to draw that image, but we're going to have this. That will be empty. That's empty, right? The solid will just be on the outside, right? So we have that empty middle. This gets harder to draw, but we have that empty middle, and then we have that solid around the outside. So maybe you can envision it, maybe you can't. It really doesn't matter when it comes to finding the volume. Alrighty? But in this case, each cross section is still perpendicular to the x-axis. And what is each cross section this time? If I were going to draw a cross section, we'd have this outer part, but then there would be this empty middle, right? That empty middle. So that shape is not, it is a circle, but it has a hole, a circular hole in the middle. Okay, we call that a disc. I'm sorry, we call that a washer. It's in the shape of a washer, okay? A circle with a circle hole. Okay? So to get the volume of that solid, we want to take the area of a circle with a circular hole. I call that pi times the big radius squared. That would be this radius. And we need to subtract out pi times the little radius squared. Okay? So we're going to have a big R and a little r in most of these. Okay? We always do top minus bottom. If we're doing a dx, right minus left. if we're doing a dy. Okay? These are called volumes of revolution. Okay? So, pi big R squared minus pi little r squared dx, or pi big R squared minus pi little r squared dy. If you have a dx, you're going to need x boundaries. If you have a dy, you're going to need y boundaries. If you have a dx, big R is going to be top minus bottom. Little r will be top minus bottom. If you have a dy, instead of top minus bottom, right minus left. Right minus left. Alrighty? Okay, let's do some examples. Oh, well, I forgot that I had this in two separate ways, but I'm just going to go with that. Alright. Okay, do some examples. We have 0.669 or 63.670. Alrighty. This time we're going to revolve that solid around the line around the y-axis. Y-axis. So clearly we have a vertical axis of revolution. So big R will be the distance from the axis of revolution to the far side of your region. We're not going top minus bottom anymore. We're going to be going right minus left. This is your big R. Little r is from the axis of revolution to the close side of your region. That is all whole. Okay. Our curve is y is equal to x squared. But if we have to do right minus left, we have to solve for x. So x will be the square root of y. This is the line x is equal to 2. Okay? The y-axis is the line x is equal to 0. So integral pi big R squared minus pi little r squared dy. Big R is right minus left. 2 minus 0, or just 2. Little r, right minus left, square root of y minus 0, or just square root of y. The boundaries are y boundaries. The lowest y is 0, the highest y is 4. So 0 to 4, pi times 2 squared minus pi times the square root of y squared is just a y. And we get 25.132. Let's take that same region and revolve it around the line x is equal to 4. X is equal to 4 is way out here. X is equal to 4. So from the axis of revolution to the far side of your region is our big R. From the axis of revolution to the close side of your region is little r. Pi big R squared minus pi little r squared. Still doing a dy because we have right minus left. So right is 4. Minus left is the square root of y. Right minus left for the little r is 4 minus 2. Remember this is x is equal to 2. And remember that this is a distance, and the distance between 2 and 4 is 2, yeah? And we're still going from 0 to 4. Okay. Math 9, 0 to 4. Pi times 4 minus the square root of y squared minus pi times 2 squared. (41.887) or 41.888. All right. Note that there is a pi in each of these. We could easily take the pi outside of the integral. I like to leave it in, and here's why. I like for students to see every time they do it, I like them to see pi r squared minus pi r squared. It drives home the fact that we have circle minus circle. Pi r squared minus pi r squared. Okay? So you'll see me keep using that, even though I know that we could take out a pi. Alrighty. Let's now consider the region S bounded by the graphs of 1 plus square root of x, y equals 1 plus square root of x, y equals 1, and x equals 4. Okay, now we're going to graph this by hand. The square root of x curve plus 1, right? Y equals 1, x equals 4. So this point right here is the point 4. If I put 4 in for x, I'll get 3 for y. Okay? Let's find the volume when we revolve this around the line y equals 3. So y equals 3 would be right up here. From the axis of revolution to the far side of your region is big R. From the axis of revolution to the close side of your region is little r. The volume will be pi big R squared minus pi little r squared. And each r is top minus bottom. 3 minus 1, 3 minus that curve, 3 minus 1 plus square root x. So we'll be careful when we're putting that one into our calculator. And we are going from x equals, what's the leftmost x is 0. The rightmost x is 4. Okay, Math 9, 0 to 4, pi times 2 squared minus pi times 3 minus parentheses 1 plus square root of x. Close that parentheses, close the parentheses on your little r, and then square that whole little r. Just be careful putting it in. Clean it up first if you want to. So 41.887 or 8 at the end. Okay, a couple more. We're going to take our basic parent parabola and our basic cube root function, find their intersection. If you are unsure, stick that guy in your calculator. X squared and cube root of x, x squared and cube root of x is x to the 1/3. Zoom 4. Where's the region? The region is right here. If I want to zoom into that region, the easiest way I know of is zoom box. So hit zoom. The very first thing there is box. Hit box. Oops, shucks. Let's do that again. Go back to the graph. Calc. Oh gosh, not calc. Zoom. Zoom box is number 1. Okay, this allows you to make a box around whatever you want to see more clearly. We hit an enter when we have a corner of the box, and then you go to another corner of your box and hit enter again, and it zooms in right on that box. Love it, love it, love it. So I know that we have a region that looks something like this. I know this is y is equal to x squared, and this is y is equal to the cube root of x. They intersect. I already know where they intersect because 1, 1 makes this, satisfies both equations. So I don't have to go and do second calc intersection when I already know what the intersection is going to be. Okay, we're going to take that region and revolve it around x equals 2. X equals 2 is out here. So we are going to have, from the axis of revolution to the far side of our region is big R. From the axis of revolution to the close side of our region is little r. We're going right minus left, so instead of y equals, we need x equals on both of these. Okay? For the volume, pi times big R squared minus pi times little r squared, dy. Right minus left for big R. 2 minus, that was our cube root, so 2 minus y cubed. For little r, 2 minus x squared, the x squared curve, so 2 minus the square root of y. And lastly, we need y boundaries. The lowest y is 0, the tallest y is 1. And to our calculator we go. So, let's see, Math 9. 0 to 1 pi times 2 minus x cubed parentheses squared minus pi times 2 minus the square root of y all squared dy. 4.113 or 4.114. Alrighty, FRQ time. This is what an FRQ might look like. I am going to begin by putting F into Y1 and G in for Y2. Okay, I'm going to graph that. Zoom 4. Zoom 4 is back to my normal graph. Okay, and that's great, but I want to see my high point there. I'm going to go to my window and go higher on my y's, maybe to 10. Should be way higher than I need it to be. And it is. I'm going to box this. So zoom box. Enter. Oh, hope I can get that. Let's see. Okay, that's pretty good. I'll take that. Looks very similar to the picture provided for us, yes? Okay, first up we're going to find the area of R. Area. Integral, top minus bottom. What was on top, what was on the bottom? F was on top, right? So f of x minus g of x dx. What are our boundaries? They gave me the boundaries, 0 and 4. They are not going to try to trick you. If it's like this, it is actually at 0 and 4. You could put 4 in for x and make sure, but I know that that's going to be 0 and 4. So we'll have Math 9, 0 to 4, y1 minus y2. $25.945. Part B. Region R is now the base of a solid with cross sections perpendicular to the x-axis. That's good, we get to keep our dx. That are equilateral triangles. What is the volume? Okay, equilateral triangles, so square root of 3 over 4 is our multiplier. Top minus bottom squared. F minus G squared. Yep, still 0 to 4. Math 9, 0 to 4. Square root of 3 over 4 times y1 minus y2 dx. 11.2344235. Alrighty, last one. Now we're going to take that region and revolve it around the line y equals 8. Y equals 8. Well, y equals 8 is somewhere up here, yeah? So we're going to have a big R and a little r. Big R. Little r. Big R is going to be 8 minus g of x. Little r is going to be 8 minus f of x. So pi big R squared minus pi little r squared. Big R, like I said, top minus bottom, 8 minus g of x. That was on the bottom. Little r, 8 minus f of x. That was on top. Still 0 to 4. Oops. Math 9, 0 to 4. Pi times 8 minus y2 squared minus pi times 8 minus y1 squared. Oh, and that is volumes of revolution using the disk and washer method.